Okay, in this video, we're going to continue our work with working with that quotient rule. And what I want to look at here is the square root of 17x over the square root of 100. Well, 17 is a prime number. I don't have any pairs in that. And the square root of 100, that is perfect. In fact, when you look at this denominator, you've got a perfect square. When you look at this denominator, that 81, not the y cubed, but the 81 is a perfect fourth root of 3. The perfect fourth root of 81 is 3. And then here you've got a square root of 144. And here you've got a square root of 2, but these two things are going to work out because you're going to be able to divide them out. So what we're looking for is perfection in the denominator. Can I get that denominator to be perfect so that there's no more radical in the denominator? Radicals in the denominator are from this point forward not allowed. Not allowed. Just like you can't have negative exponents in your final answer, can't have radicals in the denominator. So I'm going to rewrite this first problem using our quotient rule. That's the square root of 17x over the square root of 100. And we're going to accomplish getting that radical out of the denominator by just doing the arithmetic. The square root of 100 is 10, and that's our answer. The square root of 17x all over 10. Now the next example, before I take that fourth root of the denominator, I do need to simplify the y to the 11th over y cubed. So I'm going to rewrite this as the fourth root of y to the 8th over 81. And then I'm going to take the fourth root of y to the 8th and the fourth root of 81. And I get y squared in the numerator and 3 in the denominator. Okay, you go ahead and try this next one. And if you're feeling really confident, try the example as well. And when you press play, I'll come back and I'll show you the answers for both. Okay, the try was 5 times the square root of 5a all over 12. And the answer to the one on the right, I'm going to show a little bit of work here. This one, I can't find the square root of 2. Not without a calculator, and we're not using calculators. So I'm going to rewrite this one before I actually do any calculation. 24 divided by 12. 24 divided by 2 is 12. Gave that answer away. And then x cubed over x to the 13th over x cubed. X to the 13th over x cubed is x to the 10th. And then y to the 5th is just sitting there by itself. So the square root of 12, we're going to take 12 and break it down. 2 goes into 12 6 times. 2 goes into 6 3 times. And I've got a pair of 2's. So a 2 will go to the outside along with an x to the 5th, y squared. And then I'll have the square root of 3y left over. Okay, here are 2 more problems. If you want to give yourself a try on these, press pause and then come back and check your work. Okay, on this first example, I would take the 150 divided by 2 and I would make that 75. And then I've got x to the 15th and y to the 4th. So I'd simplify the y's for sure. So y to the 7th over y cubed is y to the 4th. Now we've got 75, we're going to break it down. 3 goes into 75 25 times, and then 25 is a pair of 5s. So a 5 will go to the outside, along with 2 goes into 15 7 times. That would be x to the 7th. 2 goes into 4 twice. Now our leftovers, I have a 3 left over. So that was left over, that 3. And then I had an x left over. And then the try, we should get the square root of 27, x to the 6th, y to the 4th, z to the 9th. And that's going to be 3x cubed, y squared, z cubed, times the square root of 3. I think I made a mistake here. I did. 2 goes into 9 4 times. And that's with a z left over. So 2 goes into 6 3 times. 2 goes into 4 2 times. 2 goes into 9 4 times with 1 left over. And that's how we get our final answer. Now, rationalizing the denominator is a big deal when we're working with algebra. So just knowing how to rationalize when we're talking with radicals is very, very important. So what I need to do is I need to multiply this fraction by a factor of 1. Because when I multiply anything by 1, it doesn't change its value. It just changes what it looks like. So here I've got 6 over the square root of 3. This square root of 3 is irrational. That's a bad thing. So this denominator is irrational. An irrational denominator, no bueno. That is bad. So how do we make that denominator rational? We are going to multiply by the square root of 3 in the denominator. Because if I do that, then I'm talking about a square root, and I've got a pair of 3's and nothing left over. So that means no radical will be left over. But if I multiply the denominator by the square root of 3, I have to multiply the numerator by a square root of 3. So that really what I'm doing is multiplying by 1. And if I multiply my number, this 6 divided by the square root of 3 is a number. When I multiply this number by 1, I change what it looks like, but I don't change the value. So this is going to become 6 times the square root of 3 in the numerator over 3. Now the numbers on the outside can be reduced. Numbers on the inside with numbers on the inside can be reduced. We are looking at the outside numbers, so 6 divided by 3 is 2, so we've got 2 times the square root of 3 for our answer. We're going to do a few of these, so let's do another. 1 over 3 times the square root of 2. Now the irrational problem is that square root of 2. So I'm going to multiply by another square root of 2 in the denominator, and then I'll also do that in the numerator. So then I'm multiplying by a factor of 1. The square root of 2 times the square root of 2 gives me 2 2's in a square root, and I'm looking for groups of 2 when I have a square root. So I'm going to take one of those 2's to the outside. So I get 1 times the square root of 2 in the numerator over 3 times 2 in the denominator. And that's going to be the square root of 2 over 6. Okay, you try the next and then come back and check your answer. Okay, I'm going to multiply, welcome back, the denominator by the square root of 5 and the numerator by the square root of 5. That's going to give us 7 times the square root of 5 over 5. Now, sometimes the denominator is a little bit more complicated than just something like a 3, a 2, or a 5 underneath the radical. Now we've got this 12 underneath the radical, and there's lots of things we can do here. Lots of different things that we can do. One of the things that we can do is we can reduce the square root of 6 over the square root of 12. That's one thing. Another thing is that we could just look at the square root of 12 and we can break it down and do that. But because 6 and 12 are both under the same radical, they're under a radical with the same index, we can reduce the numerator and the denominator. So this is going to be the square root of 1 over negative 3 times the square root of 2. So the square root of 6 over the square root of 12 became 1 over the square root of 2. And I say 1 because the square root of 1 is just 1. So 1 over negative 3 times the square root of 2. Now that denominator has that radical 2, and I need one more to make a pair. So I'm going to multiply by the square root of 2 in the denominator and the square root of 2 in the numerator. And that will give us a final answer of the square root of 2 over 3 times 2, negative 3 times 2, which is negative 6. Now I would move that negative to the numerator, so I have negative square root of 2 over 6, and then just bubble it or box it, and we're good to go. Okay, you see if you could do the same thing here. Does 10 and 18, since they're both under a radical, do they reduce? See if those reduce, and if they do, try and reduce them. Okay, welcome back. I've reduced these. I said 2 goes into 10 5 times, and 2 goes into 18 9 times. And then 2 times the square root of 9, that's the same thing as 2 times 3. And 2 times 3 is 6. So I didn't even have to rationalize that denominator. It just worked out on its own, just by reducing the 10 and the 18. Okay, let's look at 9 over the cubed root of 25. You're probably thinking, I just need to multiply by the cubed root of 25 over the cubed root of 25. But that's not going to work because I have 1, 2 5s, 2 5s here, 2 5s here. That's 4 5s altogether, but I only need 3 of them. I just need 3 of them to get a perfect cube down here. So this is not going to work. So you really have to think. How many more 5s would I need in the denominator? I'm looking for a good colored pen here. This is a fun pen. 9 over the cubed root of 5 times 5. Well, I've got a pair of 5s. I just need one more. So I'm going to multiply by the cubed root of 5 over the cubed root of 5. And that gives us 9 times the cubed root of 5 in the numerator, all over 5 in the denominator. Okay, in this next example, I've got 2 over the 5th root of 8 is 2 times 2 times 2. That's 3 of them. To have a perfect 5th root, I would need a group of 5. So that means I'm going to need 2 more. And I'm going to have that 5th root in there because that's the index that we're working with. Now, if I multiply the 5th root of 4 in the denominator, I have to multiply that by the 5th root of 4 in the numerator as well. So the numerator is going to be 2 times the 5th root of 4. And the denominator is just going to be a 2. Well, what's really nice here is that these 2's cancel out. So our final answer is just, I'm going to write my final answer right here because I don't have room, is just the 5th root of 4. The 5th root of 4. Now I have a feeling that we're getting close to some tries. Maybe not. Let's see if you can try this. So go ahead and try this one. Try this one. Try this one. Even though it's an X, see if you've got it because it's all about the concept. I think that if you get the concept, then you should be able to try these first two problems at the top, these 2 problems at the top, and come up with something. Okay, if you didn't press pause because I'm going to go over the answers. So the cubed root of 2, I would need groups of 3 2's, so I need 2 more. So I'm going to multiply by the cubed root of 4 in the denominator and the cubed root of 4 in the numerator. So I get 4 times the cubed root of 4 over 2, because the cubed root says you're just needing groups of 3. So I've got 1, 2, 3 2's underneath the radical. So I bring that 2 out with nothing left over. 4 divided by 2 is 2 times the cubed root of 4. And this is going to be our last one for this video, and then we'll come back and finish it up finish up those last 5 problems in another video. Okay, this last example, I need a pair of x's, so I'm going to multiply by the square root of 1 more x. And in the numerator, that gives us 3 times the square root of x. And in the denominator, it gives me 5 times x. Now, nothing reduces. So that's my answer. It's just 3 times the square root of x over 5x. Now, like I said, in the next video, we'll come back and we will address these last 5 problems from the notes.